to do this in class yesterday because I wanted to be present when you were doing this so that you just didn't leave them blank. Because once you leave one blank, you leave the next blank, you leave the next blank. It wasn't going to do you any good. And I want to make sure we go over each problem because it's not that bad. Now, number 39. The U.S. Senate Select Committee on Ethics, we started with this one, right? Has 6 members. Circle, underline, something with the 6 members. Each member is equally likely to serve in any of the positions. All that means is, here's a spinner. Each section is equally likely to be picked when I spin the spinner. So far, that's cool. What is the probability of randomly selecting a chairman and a vice chairman? And you say to yourself, does order matter? Does it matter if you're chairman or vice chairman? Oh yeah, it would matter to me because I got to be chairman, not vice. So does it matter? Order matters. When order matters, you're a permutation or your line. Whichever one works for you. I happen to like the lines because if you have a hard time flipping to the permutation, the lines are really helpful. You have 6 members. How many choices do I have for the first position? No, how many of how many can I pick from? 6. So I pick A. How many are left to pick from? 5. And these I multiply. This is your 6 things taken 2 at a time. Sometimes after you do the lines, the P is easier to write. So 30 different ways I can select a chairman and a vice chairman. That means AB, BA, CA, AC, all of these, right? I want to know what is the probability that when I select this group, it really was the chairman and the vice president. A and B, let's just say A and B, are my chairman and my vice president in that order. How many ways is this going to occur? One time. 1 over 30. You needed a probability. I'm not real fond of the way they say what is the probability of randomly selecting. They probably should have said it better, like they could have asked you how many ways could you have a vice president and a president, and then what is the probability that you selected that exact pair that were president and vice president. Maybe they could have worded it a little bit differently. But do you see where we're going with this? Okay? In my mind, if I'm thinking combinations, what's the major difference for combinations in this? Aaron. Order doesn't matter on a combination, which means does it matter if I make it a vice president and a president? No. So I can't possibly have a combination on this because I would say committee of 2. Just send me 2 people from this committee. But I need them to be in specific order. So first thing I say, order matters. Okay? 42, and stop me if you're still not seeing it. With another problem with going through these problems like this, they jump around. They go from like one thing to the next, and they do that for a reason, so you're constantly thinking about it. A pizza shop offers 9 toppings. So maybe they have onions, mushrooms, sausage, pepperoni, meat, chicken, all these different things, that tomatoes, olives. They have 9 of these things. So you call and you order your pizza. And you say, I'd like a pizza with these 3 toppings, pepperoni, onions, and mushrooms. Does your pizza place ever say to you, oh, what order did you want me to put them in? No, they say, okay, you get a 3-topping pizza. Pepperoni, onions, mushrooms. And I say, wait, I wanted pepperoni, mushroom, onions. And she said, yeah, that's what I'm giving you. Pepperoni, mushroom, onions. So order does not matter. Order does not matter. If order does not matter, I got combinations. Okay, the first thing, order matters, I get a P. Order doesn't matter, I get a C. Thank you, Melissa. Okay, how many different pizzas can you set up with 3 unique toppings on them? So I could do onions, mushroom, sausage. I could do pepperoni, mushroom, sausage. I could do cheese, chicken, mushroom, sausage. I can keep going like this. What I won't get is sausage, mushrooms, onion in my combinations. I just get them like this, right? So therefore, I do 9 things, C3. I want them combination, any order. I get 84 different pizzas I could make with any 3 of these toppings on it. How many times do I get a pizza that has onion, mushrooms, and pepperoni on it? How many times will that happen? Once. Because it won't happen like this. Because that's when order doesn't, and that's when order matters. When order doesn't matter, it's only going to happen once. So since they asked for what is the probability, I got to do this first. Find out I can make 84 different pizzas. Unique pizzas. But only one of them is going to be pepperoni, onions, and mushroom. Okay? So if you need a probability, then you make part over whole. 1 over the 10. You make 84 different ones. Does it make sense? Yes? Speak to me if it doesn't. Because sometimes we can break it down and look at it on a smaller level, where we could actually make the pizzas. You know, like maybe pick 6 toppings, make 2 each. And then you could see how many you make. You could pick the one that you have. The office of President, Vice President, Secretary, and Treasurer for an environmental club will be filled from a pool of 14 candidates. That means out of 14 people, I'm selecting these 4 positions. Now read the rest of this first. 6 of the candidates are members of the debate team. So I have 6 debate team members out of how many candidates? 14. Well, they didn't tell me anything else about those members. So either they're debate or they're not debate. I'm just going to say non-debate. Start like that so that you know what your makeup is of your group. What is the probability that all of the offices are filled by members of the debate team? Did they say they needed them to be in a special order? Did they say, like, what order can I put a president, a secretary, a treasurer of the debate team in? Order does not matter. Now, here was the tricky part. Normally, yes, we lay out a president, a vice president, a secretary, a treasurer. Normally, order matters. But the way they asked it was, what is the probability that all of the offices are filled? Filled in any order. It doesn't matter what order they came into. If they're just filled by the debate team. So you have 6 candidates to choose from the debate team. You want how many positions to fill? 4 positions in any order. So you want C, combination 6 things 4 at a time. Now, that's going to tell you how many ways you can pick those 4 members from the debate team. How many ways? What is the probability? Probability is part over whole. So your bottom number comes from this. This is your denominator. Your denominator says any 4 out of the 14. That I like to call it the generic brand. It doesn't matter who is in that group. Any 4. So technically, this is what it's going to look like. There's your probability. The specific over the generic. The part over the whole. Specific, I want 4 debate team people. Generic, I want any 4 people. Does that make sense? That's probably one of the hardest concepts to get.
What is the one, the generic one going to be with an order?
No, because it doesn't matter. See, what happened in this one, Nick, they threw us a little curve. Normally, yes, we say 4 positions, president, vice president, secretary, treasurer, and order matters.
I understand why the top one, like 64 is the top
Okay.
one, but the bottom one is still the same.
The bottom one, your probability is always part over whole. You know how we did your pizzas and we found there were 84 possible pizzas to do? How many possible combinations of 4 people are there? That's what we're saying. How many possible 4-team combinations from anybody, from your whole 14? That's your generic. The part that your specific part is from only your debate team. Okay? It is a tough one to work through, but be careful with your probabilities. Okay, the next one. B. What is the probability that none of the offices are filled by members of the debate team? Well, if 6 are debate, 8 are non-debate. So I want to find out how many ways can I take those 8 non-debates and make groups of 4. And again, over the denominator, over any 4. These are my non-debaters. Because I wanted none from the debate team. If I want none from the 6, I got to go to the other 8. And how many groups of 4 can I make from those 8s? That'll tell me how many ways I can do that, 70, over how many combination groups I get, 1001. The bottom number is the same for both of these, and that'll tell me what my probability is. And my probability has to be higher for the non-debate team. Why? There's more people. There's more people that are non-debaters than there are debaters, right? So I have more people to choose from, more possible teams to set up. Don't be quiet. So I'm going with this. Okay, you can choose 4 people at random from a group of 1,200. What is the probability that all of them would rate their financial shape as excellent?
C.
It's a C. Good. Does it matter what order they rate it? So right away we start with a C on our paper. Now, we had to look at the pie chart. So there's a pie over here. And the excellent part is 7%. And they told you, I didn't write it, but they told you that your group consists of 1,200 people. So why do they need to tell me that it's 1,200 people? So you know which numbers to work with. So take 7% of 1,200. So out of the 1,200 people, 84 rated it as excellent. Okay, that's our first step. We're still looking at a combination because it doesn't matter what order they say. Now, how many did I want to choose? 4 from this 84 and from my group of 1,200. Look, this is my denominator right here. See my denominator? A 4 from any of my 1,200. That's my denominator part right here. My numerator is my specific piece. My piece that said excellent. How many people said excellent? 84. I'm still going to choose the same amount from both. So there's my specific over my generic. My part over my whole. The bottom was right there. A group of 4 from 1,200. Make sense? Okay. All right. The second part, I used the same chart. Did it use the same chart?
Yeah.
Yes. Use the same chart, but it gave us a different amount of people. Where do you think this goes? Any 55 out of 500. Denominator. That's the whole thing. This is your whole. Your part is the ones that said none of them said good. So I don't want good. I want everything else but good. So you have 2 choices. Add up all the things except good, or subtract good and get the rest. 68% are going to say none that they didn't rate it as good.
68% of 500.
Of 500, right. They changed the problem. They went from 1,200 to 500. So 68% of 500. 340 of the whole, this is the part, said that it's not good. Okay? It's anything but the good. So now, here's your bottom number. Any 55 from the 500. Here's your top number. Out of those 340, I want groups of 55.
It seems so easy when you do it.
But those are the steps you have to walk through.
It really seems like it's a case.
Right? I know, it's always hard. It's hard when you do it by yourself. It is always hard. But you know what? Model it. Hmm?
It's nice when you circle it and stuff like that.
And that's what you have to do. What do I always say? Always pull out your numbers because like in the other one it wrote out 6 SIX. Do we always say it? No.
I pull it out sometimes, but yeah, I put in the wrong one.
You put the, which one did you put? P?
Like, no, not P, like, I would like set it up.
So do you understand how this is going? This kind of gave you like a random 55 people from this group. This is any 55 people from this group. This is your generic, any 55. That's your bottom number. Your specific number, and they made this tricky because they said none said good. So you had to take the good out of there and do the rest. So you had 68% that didn't say good. So you had to find 68% of what? Of your 500. Yeah, this one is, it's a little tricky in the setup.
When the answer said 1.3 whatever times.
Yeah, this is
mine says 1.22 negative 10.
Yeah, e negative 10 is, that stands for exponent. So this is a scientific notation number with your exponent up here.
We just leave it like that?
In this case, absolutely, because you'd have to move your decimal 10 positions to the left. That's a lot of zeros. You have to put 9 zeros. Yes. You'd have to go all the way out here. It's probably much easier in this case to do. Like e to the negative 4, you're only having 3 zeros. It's easy. This one you would actually have to sit here and count your zeros. It's probably just easier to leave it scientific. Okay? It's a small number. Okay. Alright. This is always a good one. In the state lottery. Okay, so you all go to the local store and you buy a lotto ticket. You buy a lotto. You have to pick 5 numbers, right? Do they have to come out in a certain order? So right away we got combinations. Any order. How many combinations actually win? Well, one. Only one winning combination, right? If I had the numbers 5, 10, 15, 20, 25, 30. Oops, too many. 5, 10, 15, 20, 25. I had these numbers. They called those numbers. I won. If you had the numbers, do you still win? They're in a different order. Do you still win? You're still holding those numbers, aren't you? These are the numbers you wrote down. These are the numbers you wrote down after you bought your ticket. Did you still win?
Yeah.
You still won. But how many combinations actually are a winner? There's only one set of numbers that will win as a combination. And that's what throws you off in this problem. There's only one group of 5. Group of 5 numbers, combinations, in any order, that will win. So can there be more than one winner, technically? Yes. If I hold those 5 numbers, and TJ holds those 5 numbers, and Jada holds those 5 numbers, we are all winners, but there's only one combination that won. They didn't ask how many people win. They asked what combination. How many ways can you do this, first of all? How many ways can you choose 5 numbers? That's a pretty large one. And what is your chance of winning? If you buy one ticket, you have 1 out of, it doesn't matter, that's your chance of winning. 1 out of that, only one way that combination is going to come up. This one way stands for one combination of any of the ways that you're going to get them. Now that scientific notation number, you can either leave it like that or you can move it. That one's not as bad. It's still, look at how small your chance of winning the lotto is from picking 5 out of 40 numbers. And when they do the Powerball one,
So who gets to be the lucky person then? That's not enough.
well, you got to be the lucky one that guesses those lucky numbers. That's why they call it luck. There's no way to beat the system. It would cost you way too much money to do this. Well, if you sat and figured out every possible combination, you'd have to be assured to win at least that much money. right? If you bought every possible combination.
Let's do it. Let's team up together.
There you go. Are you going to lay out the money for us? Nick, you backing us on that one, Nick?
Yeah.
Okay. Okay. This one's a really good one. 51. This one's an excellent one. Now, let's work this out. Let me just bring this down. Okay. A warehouse employs 24 workers on the first shift, 17 workers on the second shift. So, start like this. 24 first shift, 17 second shift. How many workers did they employ altogether? 41. Somehow, this number, 41, is going to go where? In the numerator or the denominator? Denominator, that's the whole. That's the whole. So, 8 workers are chosen at random to be interviewed about their work environment. So, my first thought is, out of 41 people, I'm going to choose 8. Does it matter what order they're in? No. So, I've got a combination. Out of my 41, I'm going to randomly choose 8 people. Is that my denominator or my numerator? Denominator. Any of the 41. So, denominator. Now, my numerator says, and they were tricky with this, the probability of choosing 6 first shift workers. If you need to total this to 8, you only have 6 from the first shift. What happened to the other 2? Where are they coming from? Second shift. You might want to say, comma, 2, second shift. That was tricky. They kind of let you figure that part out. Now, when we get down here, how many first shift workers do we have to choose from? 24. And we want 6 of them in any order. N tells us we're going to multiply. 2 of these guys have to be from the second shift. And N says you have to multiply. You're going to have to put parentheses and divide by this. Do you see why we did that?
So it doesn't do
It has to equal 8. It has to equal 8. They only asked that 6 of them be from the first shift. So 2 of them had to come from the second shift. Now, if they gave us more than 2 shifts, they would kind of have to be more specific on the other part. Or they could just say first shift and you can assume the other 2 shifts together. So, the second part says, got a probability of choosing 4 second shift workers. How many are you asking to be interviewed? How many am I looking at? 8. I need 8 people to be interviewed. If I want 4 second shifts, this needs to total 8. I need 4 more. Where are they coming from? First shift. Again, my denominator says any of the 4 from any of the 8 from my 41. So therefore, how many second shift do I have to choose from? 24. I want 4 of them. First shift, I need 4 more. 17, C4. Because it's an and, you multiply.
So the numerators have to equal the denominator, kind of?
In this part. And this part. Not in this case, not in every problem. In this case, yes. In this case, because you have 2 groups you're choosing from. But not in every problem. In every problem, maybe they just wanted to select 4 people. If they wanted to select 4 people, you could do this. This has to be the same, not this piece. In this one, these both had to add up because that was my total.
So always
So the same select from both. That's a good point. Leslie has a good point. She notices that we're always selecting the same amount from the generic as we are from the specific. We got to keep it even. Oliver?
So when would you know multiply and have the 2 denominators by themselves?
You're always going to have the 1 denominator because that's the whole thing. What happens is you might have 1 or 2 things on the top. Because if they take it out of one group only, like say they only wanted 4 people. If they take it out of one group only, then I only have 1 thing on the top. If they take it out of 2 groups as they did this, I have 2 things. So it's like saying 4 second shift workers and 4 first shift workers. Now, if you remember back to the last unit, we multiply. When it's an and statement, we multiply. When it's an or statement, we add. Okay? Okay, one more. Let's hit this last one. Come on, we're almost there. This is a good one. A shipment of microwaves has 2 defective units. Well, if 10 microwaves are here and 2 are defective, what's left? 8 that are not defective or good. They're good if they're not defective, right? Okay. Now, a restaurant buyer buys 3 microwaves. 3 of these units. Does it matter what order he buys them in?
No.
All of his microwaves look the same. What is the probability that they buy at least 2 non-defective? Non-defective are your good ones. So, at least 2 non-defective says I can have 2 non-defectives, 2 good ones, 1 defective. At least 2. Think money in your pocket. If you have at least $2, you could have 2 or more. So I could have 2 or 3 non-defective. And an or says add. So you have to do this twice. Your bottom number is your generic number. 3 at any of the 10. That's my group, my bottom number. My specific said take 2 from my non-defectives. But I need 3 altogether, right? Leslie noticed we have to have these add up. So I need 1 more, and that's got to come from my defectives. And when I do this part, I can take all 3 from this. And then I'm going to add those together. This was a good one.
So, right now that's 8C2 plus 2C1, right? Not times?
No, this is still a times.
Oh.
When it happens here, because they wanted you to select 3 microwaves, Dan. If 2 of them were non-defective, you still need 1 more. So one of them must come from the defective part. So at the same time, this has to happen. Or, instead of getting 2 good ones and 1 bad one, I might get all 3 good ones. These are all 3 good ones. Okay? Yeah, always have to be careful. Whenever they use a negating word, like a not or a non, you really got to watch those.
So the second one that you multiply on the denominator has to add up to the bottom?
In this case, you're always going to have to choose the same amount, top and bottom. In this case, we had 2 different groups. That had to add up to the whole thing. This one, no, because we were able to choose it from 1 group. But in both cases, you have to choose the same amount from both. Otherwise, your probabilities wouldn't be equal. Everybody has to have an equal chance of being chosen. You have to choose the same from both, top and bottom. I'm really hoping